Okay, 3, 2, 1, it's jam.
What's up, science fam? If you're watching this, you're probably watching on your laptop or smartphone, and that probably means you haven't been moving around a lot. But when we do move around, one of the signs that we're moving around, our perspective, is that the things that we can observe change. When something moves, its position changes, you can tell. But what if it moves very, very slowly, just like when grass is growing? So when grass grows, we can't actually see the tiny movements, but if we see it, wake up the next morning, we can measure that it actually grew. So in these types of things, how can we tell that something is moving, especially if we're talking about the Earth? My name is Sir Mo, Science with Fun. Let's tackle that. We can tell when we're on something that's moving very easily if it's something that's moving quite quickly, like a car or a boat. But for big, slow movements, it's very, very hard to notice. If you lived on a giant spirit turtle, if it moved very, very slowly, we wouldn't even know that we lived on a turtle. So what if the continents themselves move? So these continents are much bigger than just individual countries, and we probably haven't even gone around the entire Philippines yet. So how would we even notice if they move? So now our topic is just that. Plate tectonics, it's Earth's surface in motion. So this week we're going to identify some theories that came before plate tectonics, discuss the evidences and the shortcomings of these theories, explain some mechanisms of movement, and look at what we expect at different boundaries of plates. So how do we even notice that the Earth's moving? Some of us can sleep through earthquakes, like me. So very difficult to notice. In fact, in the 18th century, people were very set on one way of looking at the Earth's surface. So in the 18th century, they believed in Neptunism and catastrophism. Neptunism is the theory that rocks came from the ocean. It's crystallized from the sea. Catastrophism, on the other hand, is the idea that all change is catastrophic, that Earth's surface changes in a way that is sudden and violent. So it's never gradual. It just suddenly happens like boom, earthquake, boom, volcano. So that's how generally people saw things, because they can only see change that is sudden, violent, and drastic. But one dude decided to change all that. His name is James Hutton. He opposed the popular notions of Neptunism and catastrophism. Like, nah, probably a different way. And he figured that out by looking at layers of rock and the characteristics of different layers of rock. The younger layers he found have different characteristics from older layers, but it looks like they were formed from similar processes. Okay? So he said to the Catholic Church that at the time was saying that the Earth is only 6,000 years old. If he's right, if the world was gradually formed, the Earth's surface was gradually formed, then the Earth must be much older than 6,000 years old. And that didn't sit well with people. So he said that rocks probably came from magma, from Earth's internal core, from Earth's interior. And that change in Earth's surface, it happens gradually, not suddenly as we might expect. So he put forth these ideas. Plutonism, that rocks came magma and it's powered by Earth's heat, and uniformitarianism, that change is gradual, that from the past until the present, till the future, it's always been the same slow, steady processes. That's why it's uniform, because it's been present since the remote past and until the remote future. Now, the Catholic Church didn't like that, but actually, in a way, Hutton was showing that it's always been there, the influence of something. Right? It's always been there since the remote past until the remote future. So it's not necessarily against the Catholic Church. It's just that he showed that the Catholic Church at the time was wrong. And, they don't take kindly to that. So Hutton changed things. Now people had to be open to the idea that it takes time to change. It took time for Hutton to change people's minds, and it takes time for people to see change if we're looking at the geological sphere. Now, another guy who backed Hutton up is Charles Lyle. So he developed the idea of uniformitarianism and made the assertion that continents themselves can shift their position in the course of ages. Now, when he said course of ages, that made the concept of geological time. So, geological time is the idea that geological processes happen on a time scale much bigger than human lifetimes. We can't fathom how big it is. We're like Our entire life is like split seconds compared to the geological processes time scale. Right? That's why we can't observe them very, very well. We can only look at the evidence in the geological sphere itself. So people figured that continents move. Finally, people figured, okay, fine, they move. All right, but how? So nobody wanted to put forth a theory on how they move because it's so controversial already, as it is. So this guy, Alfred Begler, had the balls to actually propose something. He's a meteorologist by profession, meaning he studies atmosphere and weather. He's also a polar researcher. He wanted to study weather in the polar regions. And he's also a certified badass. Why? Because he likes going on daring adventures. He went on weather balloons to take atmospheric measurements, so extreme elevations and altitudes for more than a day at a time. He actually set a record for longest balloon flight during his day. Of course, it's been broken now, but still amazing at the time. And he went on expeditions in the polar regions for research. And he actually died on one of them because he was resupplying researchers that ran out of food. Those researchers would have died without the food that he got to them. But unfortunately, he wasn't able to make it. Right? So, he gave his life to saving other people. Hero. And even though he's a meteorologist, he studies weather, he proposed the theory. He's well known for his theory of continental drift, a geological theory. So how did he get from meteorology to geology? So what was his theory like? So he proposed that there was a supercontinent named Pangaea. So all the continents used to be one big landmass, and it just broke apart later on, just like relationships. Panthalassa, the matching super ocean. If all the land masses were together, then that means the entire ocean was just one big super connected ocean. So where's the evidence? What made him think of this kind of theory, and what made him so sure that he wanted to present his theory to the public? So first evidence that he saw is the jigsaw puzzle fit. He saw that South America and Africa in particular were continents that looked like matchy-matchy. They look like mukhang bagay sila. Sometimes you just can't help but put them together when it looks like they look so good together. Next, he actually did some hardcore research. He found that there's some match of fossils across different continents. So again, since he was going around different places, he looked at different ways that he can modify his hypothesis. So he was actually called upon for the World War, so he had to serve as a soldier. So since he's going around different continents anyway, he's like, might as well do some science. So he figured out that there are fossil specimens, different continents, that shouldn't be possible unless they were connected to each other. Like your Mesosaurus, it's an aquatic reptile, like a fish dinosaur thing, but it doesn't have the morphology. Its fossils show that it can't possibly cross oceans in order to end up from South America to Africa. So the only way that its fossils can be in both continents is if it was closer together. Another example is Glossopteris. Now this one's a fern. It's a plant. It's a plant. It literally cannot cross oceans at all. So the only way that it can have presence in 5 different continents is if all of those continents were connected together as a single land mass. Okay? So again, this fossil match supports the theory. Next is the rock and geology match. The geological features at the edges of different continents have matches in terms of their characteristics. They're very similar to each other. The rock types and the geological features on the edge of North America and of Africa are very similar to each other, as if they were just parts of something that broke apart at some point. And the evidence that comes from climate or meteorology is the ancient climate record. So the climate record can be found in ice core samples. So drilling into the polar ice, just like what Begler did, lets you see the climate record for different stages in Earth's history. So he found that it was too warm for glaciers to form near the equator, of course, as we know now. And there was no ice age back in Earth's history at the point when he found all these different samples that were in different continents. So concluded that the only way for that to happen is if, again, they were all connected near one of the poles, particularly the South Pole. So how did the continents drift? How can he explain how they drifted? How do they move? So Wegener proposed that the driving force is tidal gravity. So the gravity of the sun and the moon pulling on the earth is actually pulling the continents and allowing it to drift or float. And that the continents plow through the ocean basin or the ocean floor. Now the problem with this is that it's hella wrong. Very, very wrong, because tidal forces aren't strong enough. Yes, the sun and the moon's gravity have a profound effect on Earth, but they aren't strong enough to lift land itself. And continental crust is less dense than oceanic crust, meaning it's weaker than oceanic crust. How can a weak continental crust go through the strong, dense, thick oceanic crust? Right? So it doesn't make sense. So Wegener's proposal was discarded, and the continental drift theory was rejected by most scientists. So how do the continents actually move? What is the actual mechanism? Okay, that's something we'll talk about in the next video. I'll see you guys next time.
Party's over.